Vijayaraghavan from Northwestern. Thank you. Yeah, this is based on joint work with Konstantin Makarychev and Yury Makarychev. So this talk is about learning probabilistic models for clustering graphs. Probabilistic models are a very popular paradigm in unsupervised learning, and using really nice algorithms like spectral algorithms, random walks, and various other algorithms of this kind, we have provable guarantees for learning a lot of these probabilistic models under some conditions about these models. The broad question that we are trying to address in this talk is whether we can design algorithms, polynomial time algorithms, for learning these probabilistic models in the presence of modeling errors, when there are modeling errors. Okay, so this is important because it's very unrealistic to assume that the data that is given to you is generated exactly according to this nice model, like a stochastic block model. And there are always outliers, modeling errors and model misspecifications. And I think it's, this notion of robustness of algorithms is a very important criterion of an algorithm. And it's as important as computational efficiency or statistical efficiency when you're looking at learning various probabilistic models. Specifically in this talk, we'll be looking at the stochastic block model. This is a simpler version of the stochastic block model than was referred to in the first talk. So here we are going to think of a very uniform setting where there are k communities, each of equal size n. So the total number of total number of vertices is capital N. And there are two other parameters, A and B. So basically, between any two vertices inside the same cluster, there is an edge between them with probability A over N. And between two vertices in different clusters, there is an edge between them with probability B over N. So the parameterization is mildly different. But the way to think about this is that A is the average degree of a vertex inside its own cluster, okay, and B is the average degree of a vertex to a different cluster. Okay, and think of M as the number of edges in the graph. Okay, you can either think of this as the average number of edges or the number of edges in the graph. And here, according in a stochastic block model, each of these edge choices are made independently at random. Okay, and there's a lot of work on learning stochastic block models, including this particular session, and this is in statistics, machine learning, and these are called planted partitioning models in theoretical computer science. And there are three broad classes of results. The first is exact recovery, where you want to find all the communities exactly, and typically you need the average degree to be logarithmic in n. The second kind is partial recovery, where you want to recover maybe 99% of all the community memberships, and the third kind of results are known as weak recovery results, where you just want to do something better than random. The partial recovery results and the weak recovery results are usually they also focus on the sparse regime. And in this talk, we'll be mainly concentrating on the partial recovery regime. So this was first looked at by Amin Koja-Auglan, and there are some nice results that tell you that if there is sufficient condition between the inside degree and the outside degree, so A minus B divided by this is essentially the standard deviation of the degree, then if this is large enough, then you can recover communities up to delta accuracy. Okay, and this will be the focus of the talk. These results are without noise, and we'll try to do this by being robust to errors. Okay, so before we proceed, you could ask, okay, how robust are usual approaches? A very common approach is spectral clustering with some pre-processing, with some post-processing, and this typically goes about by looking at the top k eigenvectors of a matrix, projecting onto it, and doing some distance clustering. And these kind of approaches are typically very brittle to noise because you can just add or delete a few edges and the spectrum goes completely haywire. And various other algorithms like those based on random walks and so on are also very intuitively non-robust. On the other hand, statisticians have looked at things like maximum likelihood estimation and various heuristics like expectation maximization for maximum likelihood estimation. And one nice property of these kind of methods is that they usually try to find the best fit model measured in KL divergence. Okay, but of course these are computationally intractable to find the best maximum likelihood solution. And the goal of the paper is to get both. Can we get algorithms for learning stochastic block models that are both computationally efficient and robust to modeling errors? And in a nutshell, the answer is yes. So we will design algorithms based on semi-definite programming plus some very simple geometric clustering of the vectors given by the semi-definite program, and we'll show that we can actually these algorithms will be robust to noise, and they'll also get essentially the optimal results up to constants even when there is no noise. okay, in the partial recovery regime. So one question before we proceed is how do we model different errors? So we'll be looking at 3 different kinds of errors. One is outliers or corruptions, monotone changes, and model misspecification. The first one is basically when there is an adversary, and the adversary has a budget of epsilon m, and the adversary can do whatever they want up to can corrupt an epsilon fraction of the edges completely arbitrarily. Okay, so there's a graph generated according to a stochastic block model. There is this budget of epsilon. The adversary splits it into 2 pieces, and then the adversary deletes an epsilon 2 fraction of all the edges that were originally there, can add some epsilon 1 m fraction of edges, so the total is at most epsilon m, and this is the graph that is given to you. Okay, so the corruptions can be very correlated, and this is actually a question that was posed by Mosul, Niemann, and Sly about whether you can come up with algorithms that are robust to these kind of changes. The second kind of adversary we'll be looking at are monotone adversaries, where the only changes that the adversary is allowed to make are either adding edges inside clusters or deleting edges between clusters. So intuitively, this should only help your case, but spectral algorithms are very tailor-made for the stochastic block model, and they fail with these kind of monotone adversaries. And semi-definite programs typically make these kind of arguments robust. Okay, so this is another kind of adversary we'll look at. And the third is model misspecification and KL divergence, where you'll just assume that the data comes from any distribution that is close to a stochastic block model. And the way you measure it is using KL divergence. Okay, so it's close up to some eta m edges, because this is the right parameterization, because eta m distance in KL divergence allows you to make eta m adversarial additions. Okay. So now what do we show? We basically show that you can get good partial recovery results even in the sparse regime, and you can tolerate up to a constant fraction of the edges being arbitrarily corrupted and so on. Okay, so basically, given an instance where there is model misspecification and KL divergence, epsilon fraction of the edges are complete outliers, and any number of monotone errors, you can recover the communities up to delta accuracy as long as this condition holds. And this condition holds, the way, I mean, it looks quite daunting, but the way to think about it is that this is the condition you would have even if there is no noise, and then you have this extra condition, okay, which depends on the noise. Okay, so this shows that I mean, you can get these kind of methods that are robust to adversarial changes, and the case for k is equal to 2 can actually come about by just adapting some arguments that were known earlier. And these also give you the optimal results, even I mean, they can also match the kind of results that are known even when there is no noise. Okay, and we also have some lower bounds that indicate that this kind of dependence is actually necessary, at least for k is equal to 2. Extending these lower bounds for general k is open. Okay, so there is some related work. So Tai and Lee looked at different kind of an outlier thing, where they try to look at a model where there is a stochastic block model, but T vertex outliers, and edge outliers are in general more general than vertex outliers, and for them to allow for epsilon fraction of them being outliers, they need the graphs to be dense, whereas we work in the sparse regime as well. And okay, there's also some related work by Moitra, Perry, and Wayne for monotone adversaries, and some incomparable works on more general block models. But let me skip this, and let me conclude. It's a very simple algorithm where you look at a semi-definite program, look at the vectors, and apply a simple greedy clustering algorithm on it. Okay, and proving that this algorithm works requires a lot more work. But let me conclude by saying that, yeah, so we can handle these kind of block models in the presence of various kinds of errors, and I think it's a very general, broad, nice question to look at in the future, where you look at robustness for learning probabilistic models in the presence of noise.